continuing with our meeting, and before presenting our speaker, we are now saying goodbye to Juan that is returning back to US, or first to Bogota, and then to US. And everyone here in Medellin, and maybe also Elena and Governor are really appreciate the efforts that Juan Rafael has done to do this activity. Actually, as I told you at the beginning of the meeting, this activity is the idea of Juan Rafael. We are the people who are receiving the benefits of this activity. So I'm personally really I really want to thank you, Juan Rafael, to push us to do this activity because I am sure it will have a permanent effect on our students, faculty members, and our friends. So, in order to thank Juan Rafael, I want to give him a present. Okay, this is just the shirt of the team. So now you are part of the team, okay? Okay.
Thank you very much, and please take advantage of this as much as you can. Thank you.
Okay. See you next year. Okay, now we want to present to Professor Juan Muñoz, who is faculty member here at the Institute of Physics, working on the galactic astrophysics and cosmology value research. Okay, thank you very much. Thank you.
So, good afternoon to everyone. I'm a little tired, so I will try to speak slowly, faster at the same time because I want to do two things in this time. Before speaking about this part of my seminar, which is not like the academic part of my talk, I want to first make a short introduction of the research group here in the university. That's something we have done from the discussion on Wednesday, and I guess that for you and also for the students, some of the students here doesn't really know much about the research group in astronomy and astrophysics, so it's going to be like a nice introduction. So let me please spend some few minutes just presenting the group, just showing you more or less what we do. You have already seen at least the talk from Jorge yesterday, and next week from Alejandra, Pablo, and Ignacio. But it's good also to take a overview of the activities in the group, just to have an idea on the general scheme and how do we work and what do we do for research here in the university. The activities of research here at the university in astronomy and astrophysics are involved in the interior of this research group, the Grupo de Física y Astrofísica Computacional, the group for physics, for computational physics and astrophysics, from which Jorge, Pablo, Ignacio, Alejandra, and me are part. This is a group that was funded in 2005, like 3 or 4 years before the foundation of the diploma program, and is currently under my coordination and is currently in a status which is certified by Consensus. Consensus is like the National Science Institution, and every single research group should be validated by this entity in order to, for example, get funding and all these things. Currently, the group is composed by 6 professors, the 6 professors working in the program of astronomy here in the university. Right now we have 4 master students, 2 PhD students, and I don't actually have a clue on how many diploma students, because we have many of them working with Jorge, with Paolo, with Ignacio, with me, in many different things. But many, I would say that more than 5 or 7 diploma students are currently doing the diploma thesis in the area of the group, concerning with some research project. Since the foundation of the group, we have more or less 30 theses. Most of them have been diploma theses. Only 2 of them have been master thesis, and 50 of them are in the pure subject of astronomy and astrophysics. The point is that by the region, the historical environment in which the group was founded, it was a mixture between computational physics, astrophysics, and computational astrophysics. And then a part of the group was also focused on only computational stuff, and a part of the works and the thesis developed at the beginning of the history of the group focused also in that line. That's the reason why from 30 theses, only 17 to 20 were developed working on astronomy and astrophysical subjects as a whole. If you count more or less by the publications of the members of the group since more or less 2005, and depending on the time they were taking part of the positions here in the university, one can find more or less 45 publications from the members of the groups, which means something like 5 papers per year as an average, which is more or less the production per year we have here in the group. And we have a lot of collaboration with different institutions. Now you have seen here Leiden Observatory, but we have also collaboration with people in Germany, in Potsdam, in Amsterdam, in Heidelberg, in the US, in University of Arizona, Universidad de Buenos Aires, in Argentina, several different places on the world, also here in Colombia, in Bogotá, particularly in Universidad de los Andes and Universidad Nacional. This is basically the face of the group. As you have seen, as you can see there are a lot of familiar faces for you. And as you can see, there are a lot of people here which are basically students. Master student, diploma. He already finished the diploma student is which is actually right now in Leiden in this internship. Professors and Carlos, which is a professor, and 2 master students. So there are missing people in this picture. What do we do? Okay, we have a web page if you want to get in deep in some of the. If you want to get in deep on the details and the activities and the research results and the products of the group, you can take a look at the web page of the group. And we have been more or less right now actively around 5 to 7 research lines. When I say active lines, it's because, as I told you at the beginning, we had a lot of computational physics, non-linear physics, and those things which are already not part of the group because they just split it up in independent research groups. But basically, the members of the group work in astrobiology, computational astrophysics, planetary science, computational physics, and high-performance computing, nonlinear dynamics and galaxies and cosmology, and Monte Carlo methods in physics. The lines which are highlighted in red color are the ones which we are actually working mostly in the current time. In the context of planetary science, we have these 3 gentlemen, which are the ones which are actually producing the most of the papers and the science in the last 2 years. Jorge, Ignacio, and Pablo. They both have PhD degree. Pablo is master in astronomy, and right now is finishing his PhD in the organization of Jorge. And right now there is a student, Mario Sergio, which is starting the master degree, his master thesis, under advisory of Jorge Zuluaga. Basically, what these people is working on, as you have seen yesterday in Jorge's talk, and you will see next week in Ignacio's and Paolo's talk, they're basically working on the habitability of extraterrestrial planets thermal, magnetic, and in general the structure of extraterrestrial, extrasolar planets. They also work on the dynamics of minor bodies in the solar system, as you have seen, for example, the recent work from Jorge and Ignacio concerning the reconstruction of these minor body of the Chelyabinski object. They also work on the properties and the dynamics of the minor bodies in the solar system, in general, the evolution of planetary and minor bodies in the solar system, and something also related to astrobiology. Some present projects which these people is working on is the rotational and the thermal evolution and constraints on the existence of super Earths and the habitability of those objects, as well as magnetohydrodynamical models and things concerned with the magnetohydrodynamical considerations and environment for the habitability of the solar planets. And here you can see a summary of the most recent papers summarizing like one of the results they have been publishing in the last year, basically. These guys are paper machine people. They are, how many papers have published this year? Four papers. This year, these people actually work quite a lot. Also, they have been quite famous because a couple of works, one of them the reconstruction of the subject from Chelyabinski. Also, they produced, for example, this picture, which was winner of the second place on this contest on visualization of data for exoplanets, and this is something which deserves to be highlighted. The second most active line in the active line of research in the group is the line on galaxies and cosmology, which is basically led by this guy here, Carlos Molina. If well, he is not member officially of the university, he's not member staff. He's also taking part of the research in this line of the group, so he deserves to be in this line. So we are basically myself and Carlos Molina, who's master in astronomy and a PhD student in astronomy. And we are working with two master students, with Fernando, who is working on simulations of survival of galactic disks in a cosmological context, and David Marina, who's working with me on the concern of the formation of globular clusters and the connection they have with the problem of the missing satellites problem in the cosmology. As I mentioned, and things which is interesting to see is that here in the university we have, in the institute, we have physics and astronomy as diploma programs, but we have also master and PhD programs. Those master and PhD programs currently allow the students to basically have formation in astronomy and astrophysics. The title is still in physics, but the thesis and many of the courses we have to see are basically focused in the subjects of astronomy and astrophysics, and also computational issues concerned to the solution of problems for research in the field. Some of the problems we face in this line of the project, this day of the group, we work basically in a kind of mixture between observation theory and simulations. We study the properties of the large-scale structure, as we will see in the matter of the content of the seminar, galaxy clusters, galaxy groups, dark matter, using simulations and observations. We do some basic dynamics of galaxies, as well as study formation and evolution of galaxies, both using observations and numerical simulations. Currently, we are working on different subjects on the evolution of structural properties of galaxies in the cosmological context, formation of globular clusters in the same cosmological context, as well as the topology and the properties of the large-scale structural distribution of mass, which is kind of useful, for example, to study cosmological parameters and all these things. As well as you can see here some of the recent papers from the people working in this line of research of the group. We have also recently acquired the Maria Alejandra Luma, which is working in solar physics. I cannot actually speak much about that because we are just going to see her seminar the next week. So I just forecast we will start having some solar physics work on that direction in the next months, in the next few years. And you can see here some the other side, I mean, the motivation of the work we have done in the university, the direction has been strongly biased by computational issues. And that's because some of the guys, members of the groups, are kind of geeks and addicted to computing science. One of the lines of working in the group is also in the direction of computational physics and astrophysics. And one of the work we are doing now is try to take techniques we use in astronomy to solve real problems in applications. This is something I'm doing with a PhD student, and there is a but there is something which is involving also Horace Global because of his skills. And it's for example to use the same techniques we use to analyze the data from CMB, from COBE, or from WMAP to solve something which is called the inverse problem for the study of propagation of waves in an anisotropic medium, which is something you can use, for example, to do exploration of petroleum and all these things in material. One can also use, for example, techniques like SPH, which is a technique one uses to do numerical simulations of fluids in astrophysics to study, for example, the stability of land in a mountain, for example, to model the flux of water in a channel in a way like people doing fluid dynamics do in a very convenient way. Just to finish, there is an initiative concerned with the development of observational skills and observational practices in the students member of the group. FACHO is an initiative taking place in this observatory, which is in place in San Vicente de Ferrer. It's a small town here, like 2 hours away from Medellin, where there is, like, I will say, the largest telescope in the country. This telescope with 63 centimeters diameter is owned by somebody, someone took the money from his pocket, booked the telescope, put it in a place in the countryside, and then allow us to use it to do some basic observations, which is something the students from the group are using just to acquire some basic experience in observation, but can also be used to do observation of very interesting but also brilliant events in astronomy, like for example variable stars, binary stars, where you have seen, for example, the study of this new nova, which has just shown up in the last few days. Those are things you can do with such a small telescope if you have the equipment, the instruments, and the detectors to do science with them. I have to mention also that not only we 5 or 6 are working in astrophysics in the university, there are also some professors here at the institute which are not part of the group of physics, part of our group, but they are also working in some fields or some topics related to astrophysics. They are Diego Restrepo, Leonardo Pachon, Antonio Nea. They are professors here at the institute, but they are, for example, members of the group for particle phenomenology. They are working, for example, in high energy physics, neutrino, supernova, cosmological models of inflation and those things, and Leonardo Pachon has some skills and works in general relativity. Also, he is member of the group for atomic physics. And also in the city, we are not the only ones working in this subject. Jaime Joseph, for example, was a professor in the Universidad de Medellin, which is another university here in Medellin, like 20 minutes away from here, and works in plasma physics and magnetohydrodynamics and stuff like that. And as I mentioned, Carlos Molina, who is not actually part of the staff here in the university, who's working in the planetarium, is also somebody which is doing kind of science in the neighborhood. So I just wanted to do this very short and brief presentation of the group, because some of the students actually might not know that this thing exists and that these lines are the ones we are working on, and they can be interested, they can take place on this research for you, for example, to take a look at what do we do, how do we summarize what we do, and more or less what is the idea of, or the plan where we plan to develop in research in the next few years. If you have any question about that, you can also discuss it at the end. Which is specific to my area, to the line of galaxies and cosmology, and which is specific to the work I actually do in the field of large-scale structure and cosmology. I'm going to present like a compilation of, it's basically 3 independent works which we managed to connect together on the study of the distribution of mass in dark matter halos, around dark matter halos, and in the large scale structure, mixing somehow the results from embodied simulations and observations from galaxy redshift surveys, just to try to make a first guess and a first study on the topology and the properties of the distribution of mass in the large scale. This is a work I haven't done alone, of course. It's mainly in collaboration with Fotamula and Stefan Doktorova in the AP in Potsdam, Andrea Macho in MPIA in Heidelberg, and some other people that I mostly work interacting with these guys. The idea is basically this one. I mean, when you study large scale structure formation, when you study galaxy formation, when you look at the space of the universe, all you can see is galaxies. If you want to trace the distribution of mass in the large scales, all you have to do is to trace the distribution of galaxies in the universe. If you want to study actually the universe, all you have to do is to look at the positions of the galaxies in the universe. And when you look at the galaxies, the distribution of the galaxies, you are somehow tracing the distribution of mass. Somehow, that's not actually the reality. Because as we will see later, galaxies are biased to trace of the mass. Nevertheless, the interesting point from the theoretical point of view is to study the distribution of the mass in the universe. Why the mass? Because the equations we use to study, for example, structure formation solve the evolution of the mass density field. So, in cosmology, specifically in the context of large-scale structure and structure formation, there is an entity which is the principal entity in the field, and it is the mass density field. The question in the problem of structure formation is which is the value of the mass density field at every single point in the space, in the universe, at a given time. If you manage to answer that question, you know where the mass is placed in different places in the universe at different times, and then you know where galaxies are going to be formed, and then you can go back from the observations and then understand what you see when you see galaxies and correlate it with the mass density field, for example. We actually know, or we assume we know, the universe is composed basically by 3 main components: dark matter, dark energy, and baryon. Dark energy is something we don't actually have a clue, but we know is dominating the dynamics of the universe in the current state of the universe. Dark matter is something we actually, with sincerity, we don't really know much about it, but we have seen it sort of affects the dynamics of galaxies, sort of acts as a gravitational perturbation on the dynamics of the objects. We can actually estimate the content of dark matter in the universe that from observations of CME represents something like around the 25% of the mass density, mass energy density of the universe. This 25% of the mass in the universe contains what we call dark matter and baryonic matter. Baryonic matter is huge, electrons and protons basically. Nevertheless, doing the census, studying the properties of the distribution of the stuff we see in the universe and studying the properties of the signal from the CMB, we can conclude that from that 25%, which we call mass as a whole, 80% of that is made out of dark matter. Only 20%, which means only 4% of the total budget on the form of mass energy density of the universe is in the form of baryons, which is going to be like this red spot here. So, in principle, the universe is basically made of 2 interesting things: dark energy and dark matter, something we just don't actually have much information about their nature, and only 4% is the stuff you are made of. Dark matter, dark energy then is actually currently, not in the past of the universe, but currently is actually very important because it's responsible for the dynamics of the universe right now. The expansion of the universe is dominated by the content of dark energy as we can measure it from the CME. Nevertheless, dark matter still is very important. Dark matter still is very important because structures in the universe are formed from dark matter, and galaxies form in the deep potential well provided by those dark matter structures. Here we can see just a slide from a cosmological simulation where we can see the way the dark matter distributes in the large scales in the universe. The way the dark matter distributes in the large scales in the universe is way too complex, because the distribution of mass in those scales is completely dominated by gravity. Gravity is a highly non-linear process in a way that is very difficult to understand it from very basic principles using analytic formulations. That's the reason why you, for example, need to use numerical simulations to study the distribution of mass and the evolution of the distribution of mass on the large scales. From the results of those numerical simulations, we can see, for example, that dark matter in the universe distributes, forming something like something that we call the cosmic web. The mass in the large scales forms like a foamy structure where you have something like filaments, high density regions, which are going to be dark matter halos and dark matter substructures, and these characteristic places, these white places here, which are basically empty regions. They are not explicitly empty regions, but in terms of the density contrast, they are basically empty regions which are basically voids. So the mass in the large scales, the mass density field, this quantity, this theoretical quantity I was mentioning at the beginning, distributes right now in the universe in a very complex way. A very important entity when you study the distribution of mass, the mass density field in the large scales, is this one, this guy here, dark matter halos, dark matter over densities. The point is this one. Dark matter over densities form first, since dark matter in principle is not invariant matter. This matter doesn't interact with the radiation field, with with the electromagnetic field. Dark matter over densities started to collapse in the very early universe. When the universe expanded and cooled down to low enough temperatures, barriers started to cool down and fell down into the potential wealth provided by these dark matter halos in the very early universe, quite after the coupling. The assumption we have right now is that since dark matter halos provide the potential wealth for gas to cool down in the interior of those halos to form stars and therefore to form galaxies, the assumption is that the properties of those galaxies should be dependent on the properties of those dark matter halos. If you didn't have dark matter halos at the beginning, you shouldn't be here. Galaxies wouldn't form if dark matter halos and dark matter didn't exist at all. So, in principle, we expect then that dark matter halos are the catalyzers in the process of galaxy formation. And that's basically the way we have to relate the distribution of mass with galaxies. Wherever you have a peak, a density peak, and an overdensity peak in the distribution of galaxies, you should have somehow an overdensity in the distribution of mass, that in this case is going to be dark matter. In general, the distribution of mass in the universe is dominated just by the distribution of dark matter. Dark matter halos explicitly are defined as the very peak in the density field, very high density peaks in the density field. Explicitly, they are defined as the virialized region of the overdensities in the density field. That means that in this region, there is a region in the very inner part of the dark matter overdensity where virialization took place. The dynamics in that region is more or less virialized, so the system has some sort of equilibrium, and then you can host a galaxy, and you can then a stable system in equilibrium that can evolve in some way that allows the formation of these kind of objects we see right now. Nevertheless, dark matter halos are not independent unities from the density field, and if you are able to solve the problem of the identification of dark matter halos in the mass density field, you are basically done in the way that you can be able to use those observations to trace and to rebuild the reconstruction of the dark mass or dark matter density field in the whole universe. What I'm going to do right now then is basically, you can study dark matter in very different ways. You can study the nature of dark matter, study the models, you can propose some model for the candidates of dark matter as self-annihilating particles which produce gamma rays and subproducts and those kind of things. That's one way. You can also study the properties of dark matter, for example, using embodied simulations to study large-scale structure formation and study the properties of these objects, which are the ones where galaxies are hosted and are formed, and then interpret those results from embodied simulations in the context stuff. You can study also the distribution of mass of dark matter in the very large scales or in the intermediate scales. Right now, I'm gonna ignore the structural properties of dark matter halos in the very inner region because I'm not gonna be interested right now for the context of this talk on the problem of galaxy formation, which is mainly the reason why we do this kind of high resolution and value simulations of the large scale structure. And I'm gonna focus only on the problem of the distribution of dark matter in the large scales and at the intermediate scales. Specifically, I'm going to show you how do we use embodied simulations to study the distribution of mass around dark matter halos, and we use it to couple it to the distribution of mass in galaxy redshift surveys to make reconstructions of the full dark matter density field in the large scales. So first, I'm going to show you how do we identify dark matter halos in observations. Basically, the idea here is you give me a galaxy redshift survey, I give you a catalog of dark matter halos in the volume of that survey. Later, I will show you briefly how do we then interpret the distribution of mass around those dark matter structures in galaxy redshift surveys, and later I will show you how do I use that information to show you where in the digital sky survey, for example, is the dark matter, where are the peaks, where are the phalanx, where are the different structures. So, as I told you then, when you look at the universe in the large scales, all what you see is galaxies. Nevertheless, you already know that the mass is distributed in the universe not following galaxies, it's following the mass itself, the dark matter density field. So the question is, how can I infer where the dark matter halos are in a galaxy redshift survey when all what I have is the information coming from the galaxy redshift survey? That means colors, spectra from the galaxy, and a measurement of the redshift of this galaxy. In order to answer that question, I'm going to make a couple of assumptions which are going to be very important. The first one is, as I mentioned briefly a couple of minutes ago, is that I'm going to relate over densities in the mass density field with dark matter halos. So I'm going to assume, as it is done properly, that dark matter halos are over densities in the dark matter density field. That's the way they are defined. I'm going to also assume that galaxy groups, agrupations with different amount of galaxies are over densities in the mean number density of galaxies, and I'm going to assume that the relation between those over densities in the number of galaxies and the over densities in the mass density field are related in a one-to-one way. That means where you have the highest over densities in dark matter, you have the highest over densities in number density of galaxies. When we look at the data from the observations of galaxy redshift surveys, you get basically a couple of numbers. Let's say you get the colors of the galaxy, let's say for example 2DF or 2MASS of SDSS galaxy redshift surveys. What you get is basically the colors of the galaxies, that means fluxes of the galaxies in different times, and spectra. And from this spectra you measure basically the redshift of the galaxy. The redshift of the galaxy is basically usually interpreted as a measurement of the distance to the galaxy, but it's not actually true. If you have a real universe, the redshift of the galaxy is going to be a measurement of the distance to the galaxy if no peculiar motion of the galaxy is happening. Nevertheless, that's not the real case when you're talking about galaxies which are members of a group of galaxies, for example, because peculiar motions decouple the movement of the galaxy from the Hubble flow, inducing perturbations on the determination of the distance through the redshift determination. And you can see here we have a slice taken from the digital sky survey for a given sample of galaxies. And as you can see here, there are some elongations. These structures, if the universe is homogeneous, isotropic, and all these things we assume in the very background of the cosmology, these things shouldn't happen. Because those inhomogeneities are pointing out to a special place, which is where the observer is, and in principle, those things shouldn't happen, shouldn't be there. Actually, those things are not there. The problem is that the way we reconstructed these coordinates, this is 3D moving coordinate projection of the different galaxies in the volume of the survey, are including the determination of the distance to the galaxy through redshift. And in this case, the redshift of the galaxy includes information of two particular movements. The first one associated with the precessional velocity of the galaxy because of the expansion of the universe, but also information associated to the peculiar motion of the galaxy in the potential, the gravitational potential well of the host dark matter halo. It results then that when you are here, if you are here with your telescope and you measure the redshift of the galaxy, which is here, if there is nothing else around this object, the redshift you measure for this galaxy is going to be a measurement to the distance of the galaxy. Nevertheless, if this galaxy is hosted on a bigger dark matter halo, the galaxy should be orbiting the halo somehow, and then this orbital motion is going to introduce a relative velocity of this galaxy, relative to the Hubble flow. This difference in the velocity introduces what we call redshift space distortions, and those things are actually those redshift space distortions. There is a problem. If you want to build a catalog of galaxy groups, you need to determine the exact value of the distance to the galaxy to be able to cluster the galaxies in the same family. Redshift space distortions destroy this information. They break the symmetry of the distribution of particles in the galaxy redshift survey, and then they avoid or they introduce a problem on the determination of the membership of galaxies to a given group. In order to overcome this problem and to be able to make a reconstruction of the membership of galaxies which are hosted in the same dark matter halo, we developed a method which allows us to use in a kind of inverse way the hierarchical method of galaxy formation to rebuild the membership of galaxies to a given group of galaxies which are by default hosted in the same dark matter halo. What we do basically is to use a kind of iteration process in which we start with a distribution of galaxies in the galaxy redshift survey. Those galaxies are characterized by positions in 3D, redshift space, coordinates, and a given luminosity. More luminous galaxies are tended to be hosted on more massive dark matter halos. So what we do is to assign to a given galaxy a given dark matter halo with a given mass, depending on the luminosity of the galaxy. Galaxies which are closer to each other merge together and form then a bigger structure with a new structural parameters, with a new set of dark matter halo properties, and iteratively, in an iterative way, galaxies start to grow from one only galaxy hosted in only one dark matter halo to galaxies, many different galaxies which are hosted in many different or in very different dark matter halos. In order to assign the masses to the halos in the galaxy redshift survey, what we do is basically to make abundance managing. What we do is to assume that, again, most luminous galaxy groups are hosted in the most massive dark matter halos. So we do like a one-to-one matching between the luminosity function and the dark matter halo mass function in a way that from the luminosity we obtain in the galaxy redshift survey, we can kind of flag the dark matter halo mass of the object of the group of galaxies in the galaxy. What we have here is the same slides we had before. Here we have the positions in redshift space of the galaxies in a given region of the galaxy redshift survey. This is for a volume limited sample defined by a magnitude of -90 in the absolute magnitude in the survey. What we have here is the projection of the positions of the same catalog of galaxies, but in this case, what we have here is not the position of the galaxies, but the position of the center of the host dark matter halo. Look at this figure in comparison with the one. The effect of the figure of good, these elongated structures are completely gone. When you are able to remove these structures, that means you are eliminating the problem of the redshift space distortions, and what you actually have here is the position of the center of the place where galaxies are orbiting around, and they are actually the positions of the dark matter halo. During the identification of groups, we can then dark matter halos, but also the mass of the halo, which is a problem to determine if you don't have much dynamical information about the galaxy group. What I'm showing here is the richness of the group, the number of galaxies which are hosted in a galaxy group as a function of the dark matter halo mass. What we see here, this behavior here, which is actually a power law on the mass, is actually very well constrained by different models, for example on halo occupation distribution, which are theoretical models of galaxy occupation coming from results of numerical simulation. And all results coming from the observations are in very good agreement with the results of this kind of predictions. You might not believe for example, the mass I obtained from this procedure for the dark matter halo. You would say, okay, I believe you are able to find the place, the center of the galaxy group, but I don't believe you can estimate the mass of the object. In order to make sure that indeed we are something a good job, the only way is to make a test. We have verified the performance of this method using galaxy catalogs obtained from embodied simulations. Using embodied simulations, you can model the process of formation of galaxies. You can make a sample of the universe in the computer. And you can mimic all these effects, the redshift space distortions, you can mimic the effects of the dust extinction, you can mimic all the physical processes you want. In this kind of catalogs, in this case we took catalogs, galaxy catalogs from the Millennium simulation, we have run all halo finder in the galaxy population, in this synthetic galaxy population, on a sample which is very much similar to the one we use to run this test in the digital sky survey. Running the finder, the galaxy and the halo finder in this synthetic galaxy population, we have found this thing. In this axis, I'm plotting the mass of the halo obtained in the simulation. That means the real value of the here I have the mass of the dark matter halo obtained by the halo finder, by the technique I just showed. And in this axis, I'm showing you the mass of the host dark matter halo of the groups I found in the simulation, but computing the mass from the simulation. In the simulation, you know a priori which is the mass of the dark matter halo, the exact value of the mass. What we have here is the result of the value for the different groups we identify in the mock galaxy catalog as a function of the original halo mass. And as you can see here, there is quite a well one-to-one relation, which is showing that actually, if in the simulation I have a halo with 10 to the 12 solar masses, my halo finder in the mock catalog is assigning for that dark matter halo 10 to the 12 solar masses. So the one which is actually provided from the simulation. The same, if you think on a dark matter halo with 10 to the 14 solar masses, I am predicting or identifying the same dark matter halo with the same dark matter halo mass. That means that in principle, when we test the method and we test our implementation in mock galaxy catalogs, the technique works not only identifying the centers and the richness and the membership of the galaxies in the galaxy groups, in the galaxy redshift survey, but also in determining the mass of the host dark matter halo, which is actually the problem. So, if you want to sell me this work, I will tell you, give me the data of your galaxy redshift survey. That means give me the colors of the galaxies, and give me the spectra of the galaxy, and I give you where in that volume of the universe are the dark matter halos, and which are the masses of those halos, which is something you cannot see. You only see the galaxies. Now you can think on, okay, what can we do with that? In order to see what can we do with that, we have to go back to cosmological simulations. Now I want to show you how do we study the distribution of mass, dark matter mass, in cosmological simulations, but not in the inner part of dark matter halos, but in the neighborhood. Because we are going to use this information. Many people have been studying the distribution of mass in the inner parts of dark matter halos. I mean, that's something which is very well known. But not actually many people have been working on this subject. How is the mass distributed in the neighborhood of dark matter halos? That's something which is actually critical, for example, for the analysis of gravitational lensing in galaxy clusters, in galaxy clusters. In order to do that, we have to go back to embodied simulations because since you don't see dark matter, actually you need to rely on something you can control, which is going to be a numerical experiment. What we have here is again a slice of a cosmological simulation of structure formation. This is something like 1 megaparsec side box, and these are slices of 10 megaparsec here. What we have here is the distribution of all the mass in the cosmological simulation. And what we have here is only the distribution of the dark matter halos. So this is all the mass, and this is all dark matter halos. That means only the very peak of the iceberg. The tip of the iceberg where the mass is highly realized and the galaxies are forming. What we have here is the rest of the mass in the mass density field. The mass which is not taking part of the realization process of the dark matter halo, the mass which is not inside the real radius of the halo, and that is not actually taken into account in many respects. Something we can see here is that the mass in the environment of dark matter halos is strongly correlated with the mass which is in dark matter halo, which is something one would expect. If structure formation is a gravitationally driven process, one expects that there should be a strong correlation between high density peaks and something which is around, which should be driving the evolution of the universe in the neighborhood of this place. So the question I want to ask right now is then, how is the mass here correlated with the mass here? How is the mass distributed in this region around a given dark matter halo in this part of the slide? To do that, I'm going to define something tricky. I'm going to define the neighborhood of a single dark matter halo. So a dark matter halo is a structure, it's just a sphere of dark matter mass, and this sphere has a size. Depending on the mass of the dark matter halo, you have the bigger the dark matter halo, the bigger the size of the halo. At a given dark matter halo, I'm going to associate an environment, defining this environment as the region of the universe which is being most affected by this dark matter halo than for any other. For example, if you have two bodies with mass here, it's going to be a place in between them, depending on the mass, the relative masses of the objects, where the dynamics is going to be dominated by this one or by this one. For me, the neighborhood of each one of those objects is going to be the region which is closer to this one, or which is actually the region where the dynamics of the neighborhood around the universe around this object is being dominated by the presence of this object. I define then around every single halo something which I call the domain of the halo, which is the neighborhood of this guy, which is something I can compute through the particle distribution in the simulation. I define the domain of each halo as just a measured distance, where the distance between different points is a weighted region between the distance in space between the dark matter halo and the points in space and the given bigger radius of the halo. One can actually prove this thing concerning weighting the local dynamics, the local gravitational dynamics, and the whole expansion of the universe in a way that this relationship tells you, okay, the most massive halos have minimized this number, and then they can just extend to larger volumes, making them that the most massive halos have the largest environment. Using then these environments, I can then compute a density profile, a density distribution for the mass in the halo and in its neighborhood. I use then this formula in which I divide the population of halos by mass and have to make a sort of tricky geometrical computation of things to compute the volume of every single particle in the simulation through a Belloni isolation. But the important thing here is that we can compute the density distribution of mass in the dark matter halo, which is going to be this region from 1 to here, and in its neighborhood, which is actually something like the correlation function between the dark matter halo and the neighborhood and the mass which is distributed around it, without repeating correlation between points. This is only the correlation, the self-correlation between the mass belonging to the neighborhood of a halo and the position of the halo itself. One can do that then for different galaxy masses, or for different halo masses and for different redshifts. And that's what we see. This is what we obtain. What we see here is the results for different the density distribution for different dark matter halos at a redshift 0. And as you can see here, we have basically the same distribution for halos at a given mass, all at different redshifts, from 0 to 4. All these density distributions have the same shape, this one here. If you look at the figures, they have the same mathematical form. We model the density distribution using this formula, which actually describes the density distribution of mass in the inner region of halos and in the neighborhood, in the outer part of the halo, for different halo masses from 10 to the 10 to the 14 solar masses in radius from 0 to more or less 20 times the regular radius of the halo, and in redshift from 0 to 4. In a way that in the inner region, the halo distributes in the normal way, following, for example, the Navarro-White profile, and in the outer region, using a damping factor which makes the density profile to couple with the mean density field in the cosmological density background. This is actually the most important part of this work. The point is here that I already answered the question. You were asking me how is the mass distributed in the neighborhood of dark matter halos. This is the way. And if you need to model it, this is the way you have to. This is the way you have the mathematical way you have to describe this data. If you are, for example, doing prediction for galaxy lensing or gravitational lensing in galaxy vertices. So now, what I want to do is to overlap this work with the previous one, where I have identified the positions at the masses of those dark matter halos. And I'm gonna do it in order to make reconstructions of the mass density field. What I want to do is then I'm gonna assume that this thing is right. I mean, if this thing is not right, first I'm gonna have a paper wrong. My thesis is based on something which is actually wrong, and I have wasted like 1.5 years working on this. But I hope this is actually not wrong. Actually, it shouldn't be. But we are gonna assume then that embodied simulations, cosmological simulations, are right in presenting you the reality on the properties of the distribution of mass in the large case. Probably cosmological simulations are not right in the very small case because there are numerical issues related to galaxy formation and those things. Nevertheless, in the outer part, large scale structures more or less well behaved. The dynamics is more or less very well understood. So this thing should be right. Our first assumption is going to be that we are right in this direction, and we are going to assume then that we can somehow describe the distribution of mass around the matter halos in the large scale structure. And second, we are going to assume that somehow in a galaxy redshift survey we are able to locate, to place dark matter halos and give a mass to that dark matter halo. That is something we already did in the first part of the talk. What we are going to do then is to use this information to convolve these two pieces of work to allow me make a reconstruction of the density field in the large scale. Basically, what I want to do is this. If you have then a dark matter halo catalog, which is going to be represented by this function, a dark matter halo catalog is defined by a catalog where you have the positions of the halos and the mass of each halo. Yeah? If you have this dark matter halo catalog and you have a distribution of mass, the way the mass is distributed around this dark matter halo, in this dark matter halo, and around this dark matter halo, you can convolve this density distribution at a given place, at every single place where you have a halo in your dark matter halo catalog, and then be able to reconstruct the density distribution in that place in space. If you then compose the reconstructed density field around every single halo, then you can build the full function associated to the mass density field. It's something like this. You have that this is the density distribution around a given dark matter halo. And you have then your galaxy or your halo catalog, and you have here a halo, here you have a halo, here you have a halo, here you have a halo, and here you have a halo. The method works such that for this halo, what I'm going to do is to convolve this density distribution with the properties of this halo in the catalog, allowing me to reproduce the distribution of mass around this object. I do convolve this density distribution with this one with this one, with this one, with this one, in a way that I can then reconstruct or rebuild the full density field when I compose the full density distribution. The way we do this, the practical way to do this, is doing a particle sampling. We then do the convolution, do the composition of the distribution of densities, the full density field in the volume of the survey. But the way we compute this thing is through a Monte Carlo realization of the mass density field. In a way that the final result we obtain is this one. A particle distribution. A distribution of particles in the volume of the survey that is tracing the full mass density field. What we have here is basically the same you get when you run a cosmological simulation. When you run a cosmological simulation, what you get is a distribution of particles, in this case phase space, in the case of the simulation, traces the distribution of the probability function, the function distribution. This is something like half of the results of the simulation, because here we have only recovered the positions of the particles in the mass density field, not the velocity information. What you see here is, for example, the complex distribution of mass in the large scale structure. You can see here the filaments, you can see here clearly very empty regions which are associated with the voids in the galaxy, in the distribution of mass in the large scales. In a way that then when you apply this technique to a galaxy versus survey, you can recover the full distribution of dark matter in that piece of the volume. And then again, the business is the one. I tell you, give me your galaxy catalog. I tell you, go with the mass distribute about the halos in that galaxy catalog. I tell you, where are the halos and which are the masses in that galaxy catalog. And with those two, I can tell you where is the dark matter in the volume of the survey you are working.
So do I understand correctly that this is independent on any large scale formation simulation that starts with the cosmic background?
This is not a simulation. Actually, this is a piece of the reconstructed density field for the data release of the physical space survey.
It's based on the data of the galaxy.
Yes. So
you have compared that with the simulation.
Yes. I will show you. So this is actually, if you were able to look at the universe and look at the dark matter in the universe, if you were able to look at the dark matter in the full data release of the digital sky survey, you will see this. This is the way the dark matter is distributed in a piece of, this is 300 times 300 megaparsec cubic in the volume of the survey. This is not galaxies. Every single point here is just dark matter. Of course, the most intense regions are the peaks associated with the centers of those dark matter halos where the galaxies in the survey are hosted. Of course, you might think, again, you have to sell this thing, because people are not going to believe that what you are doing is actually cosmological meaning. There are different ways to verify that this actually produces the same clustering pattern you have in the real universe. To do that, actually what you have to do is to compute the power spectrum or the correlation function. What we see here is actually the correlation function computed for the same reconstructed, for the same region of the dark matter halo of the galaxy versus survey, computed for two different realizations of the reconstructed density field. What we see here is the typical clustering pattern we see when you run a cosmological simulation, or when you take the observations and compute the clustering pattern from the distribution of galaxies. You see here the one halo term associated with the correlation between particles in the same dark matter halo, and here we have the two halo term which includes the correlation between two different halos which are separated at a given distance. I don't have that figure here. No, I don't have that figure here, but of course I have run the method and used, as I did for the Millennium Catalog, identifying the groups. I did exactly the same experiment using only a cosmological simulation, where I do know where are the particles distributed, where I do actually know with precision which is the mass of every single dark matter halo. And then if I use the halo catalog from the cosmological simulation and do the reconstruction on top of this halo catalog, I can recover exactly the same correlation function. So in principle, the result, the reconstructed density field is cosmological. It's not only cosmological meaning, but also reproduces actually the cosmological density field traced by the halo catalog you gave as an input. Just to finish, basically on time, I just want to then highlight a couple of conclusions and summary. So the first three things I want you to take back home is there is a way in which you can identify in a given galaxy redshift survey where the dark matter halos are and which the mass of those halos is. If you provide enough information like colors, luminosities, and redshift. That's something I have done, for example, for digital scale survey to mass, to the F6DF. In general, if you have enough information, you can do this job. Second, you can actually, or you shouldn't ignore the way the mass is distributed in the neighborhood of the dark matter halos. And if you don't ignore this information, you can use it to understand how is it distributed in the outer part of the dark matter halos, and you can use it to see how the dark matter is distributed in the large case. In a way that if you provide me with a halo catalog, that I already tell you how to use it, I can tell you how is the mass distributed in the very large case. Basically independent on any assumption. This method basically doesn't assume any model. It's basically model independent. The only dependence of this method on the model is on this. If you change the cosmology, of course, the correlation function in the outer part of the halos is going to change. That in a way that these parameters are cosmology dependent. Actually, they are cosmology dependent. But in principle, if you can make a cosmology dependent model for this parameter, you can, independent on any cosmological model, make a reconstruction of the distribution of mass in the very large scale and that's all I want to do. Question?
Can you go 2 slides back to the picture? I have a question there with concerning the filamentary structure. Sorry, I'm having this confusion. Maybe I can illustrate my point by using an analogy with star formation. Well, we know stars form from molecular hydrogen, let's say, and I can make a distribution of where all the young star clusters are. When I then look this like threshold for distribution of molecular hydrogen, I find a web of very filamentary structure. And everywhere where it exceeds a certain threshold, then sort of the cluster forms. Okay? And strikes me when I look at dark matter simulation that I see similar filamentary structures. But they're not the same. Again, like in the star formation case, they're more connected, whereas the clusters themselves are isolated. And if I now compare that image with what I think I remember, then what I think I remember has more connections between the dark matter things.
Yeah.
Which are missing here.
Yeah, I mean, they are not actually quite visible here because of 2 reasons. First, because if you want to really see a lot of filamentary structure, you need to have a quite large volume, not only 2 or 3 megaparsec inside, like this one. Because a typical filament has 50 megaparsec long, which is basically the distance between 2 big structures in the
What's the size?
This is 250. So in order to be able to look at a lot of filamentary structures like the ones you see in the random simulation or in Bolshoi simulation, this simulation, you actually need quite a bit more volume scope to be able to look at them. Nevertheless, you can see those things here. The other thing is that actually defining filaments is tricky because they depend on the density threshold you use to define. Actually, the density threshold here is not too low, but it's not very high, but it's not low enough to allow us to see a large number of tiny filaments, like the ones connecting galaxies in the scales of the local group or the local cluster or the local supercluster like structure. Yeah, nevertheless, one can actually see filaments in this kind of reconstruction. That's one thing, and the other one is that particularly this slide is also quite thick. It's also 250 times 250 times 250. So when you have 250 megaparsecs in projection, you lose a lot of perspective because the projection erases a lot of structure. So when you build this thing using slices of 50 megaparsecs, for example, the filamentary structure highlights, enhances the view of these things. No question? Oh, was my teacher? Or was the comment? So, I guess we have the lecture at 4.
Yeah.
So, be please here at 4 or at least 5 before to be ready for the test. Yeah? So, see you here in 50 minutes, 45.